Right, okay, so we've got 1.5, an 8, 5 and 2, and we want to write those in the format 6 bits for the mantissa, 4 bits for the exponent. Okay, so the starting point when we're going from a decimal representation to a floating point is to just try and write down the number first. Okay, so we put ourselves a boundary point, so we're doing the 1.5. And we just say, right, okay, let's just put some column headings in so we got some space to write numbers down. Obviously making sure you've got column headings that are going to let you write the number down. It's a positive number, so we need to start, whenever we're writing down numbers, we always start and put our sign bit in. So always put that one in first, and then we need to write down 1.5. So we've got 1.5. Fill all the rest of the things in with zeros. But that's not in floating point, that's a fixed format. So we need to make sure, to put it in a floating point format, we need to normalise. Okay, and to normalise we want the first 2 bits to be different. So with a positive number, that should be a 0 followed by 1. 1 being the significant bit. Okay, so if we look here, the boundary point is currently at that position, but we need to move it to here. Okay. You can think of this in a couple of different ways. You can say, right, well, it's a positive number. Let's find the last 0. That's where it's going to start, which might be a quicker way of doing it. And say, right, okay, that's where I need to move it to. So if I go, right, sign bit of 0, well, that's the last one. So that's chaff. We don't need it. Doesn't mean anything. That's where we're going to move the binary point to. Make sure you put the arrow on. Okay, otherwise you'll get confused because you've got 2 points. So you need to know I moved it that way. Okay, so my mantissa part we've now got sorted. It is going to be 0.1100. We can't leave it like that because we need 6 bits. So we need to pad with a 0. So that gives me the mantissa. And you will get a mark for getting that correct. We now need to work out what the exponent is. Now with this one, we moved 1 position. So the exponent's value is 1, but we need to know what sign it is. Okay, so it's got a magnitude of 1, what sign? If we move to the left, so we shrunk this number, we need a positive exponent. So the exponent in this case will be positive 1. Okay, so that is 1.5. So I'll write that one down here, because we'll use that later when we do the arithmetic. So that's 0.1000. Everyone happy with that one? Right, okay, let's do the next one, 8. So I'll just rub all that out. I'll leave my column headings on so I don't have to keep rewriting them. Okay, so I've got my binary point. 8th is a positive number, so I'm going to put a sign bit of 0 in there. And I want to write an 8th. Well, luckily that's a column heading, so that's dead easy. So an 8th there. I need to fill all the rest in with zeros. Okay, again, that's not in floating point, that's a fixed format. I need to now normalise it. So I'm going to look for the sign bit and I'm going to keep going until I find the last sign value, which is 0 in this case. So that is where my point needs to go. Okay, so it's currently there, so I'm going to move it 1, 2 places to get to there. Okay, so that is now my mantissa sorted, so I can write that down. So I write down 0.1, but I've got another 4 bits I need to fill in. That's my mantissa. Okay, now I need to sort the exponent out. So in this case, I moved it 2. So my magnitude of my exponent is 2. What sign is it? Well, I moved right, so I make the exponent negative. Okay, which I know, because I've done enough of these, that is negative 2. But let's just prove it, because it's held in 2's complement. So let's write down 2. And do 2's complement to get negative 2. So we go flip, flip, find the last one, write it down as a 1, everything else stays the same. And that's my exponent. So if you do it this way, sort out the mantissa, find out what size the exponent is, and then work out what sign it is. Okay. Generally, you can do it another way. you can say if the number's bigger than 1, your exponent will always be positive because you've got to make the number bigger. If the number is less than a half, your exponent will always end up being negative because we've increased the size of it when we normalised, and we'll need to shrink it. That's what negative means. Negative means make it smaller. Remember, this is the equivalent of writing down numbers like this. 10.5 times 10 to the 4 and 10.5 times 10 to the minus 4. Which is the bigger number? Yeah, that one. Because that one, whoa, that's going to get quite small. Because this is still an exponent, it's just in decimal, isn't it? Okay, so that's all we're doing. We're just messing with the same things. But we're doing it in binary. Because we can make do with noughts and ones. We don't need all those other digits. So stupid. Right, so I'll write that one down. So an 8 is 0.1 in this format. 1110. Right, okay. Next one is 5. Remember, it is not wrong to store whole numbers in floating point format. Okay, you can do that. And if you get asking the question what would be a suitable format to store a certain value, floating point might be suitable. Depends what you're going to do with that number. If you're going to do some division with it and you want some fraction, then float might be a sensible number to save you having to like convert and cast and things like that. Right, okay, so I've got 5 this time. If I was to use this structure I've put on the board and wrote 5, what could you tell me about that number? Go on, Jack. It's negative, so we need to put another column on, don't we? So we can write down a positive number. The rest of them can just be filled in with zeros. So that's 5, so now we need to normalise it to get it into this floating point format. Looking from this direction, I've only written 1 0 at the front, so that's where we're going to start. So I need to move the binary point 1, 2, 3 positions, put it there. So my exponent is going to be 0.1, my mantissa is going to be 0.11, and then 2 O's. I can't have all of them, I've only got 6 bits. Okay. Remember, that's the precision of the floating point number. The number of bits in the mantissa is how precise we can hold it. We normalise to try and maximise that precision. Okay. Right, okay, so we've sorted out the mantissa. Let's look at the exponent. We moved it 3, so its magnitude is 3. We moved it to the left, so we're going to make it positive 3. So the exponent is going to be that. Okay. Right, so let's write that one down. So 5 is 0.101. Can anybody actually look at the floating point and read the number without doing all the work? It's not so easy. So that would be 5 eighths. So 3 would be multiplied by 8. So you can sort of do it. I wouldn't advise doing that. I'd advise doing it all a long way. Remember, we've got no calculator, so we can't cheat. Your calculator won't be able to do these anyway. Because it won't use this format, it'll use a proper floating point format. Not that it'll show you that in binary, I don't think. Okay, the next one is 2. So, put a sign bit of 0 because it's positive. Write down 2, fill all the other ones in. We need to normalise it again, so just work from this side, find the last 0. Because this is a positive number, we're looking for zeros. And that's where we want to put the binary point. So 1, 2 positions. Okay, so my mantissa is 0.10. And then I need another 3 spaces filling in. Okay. I've moved it 2, so my exponent's magnitude is 2. We went left, so we need to make it positive. Okay, because we started with a number bigger than 1, so the exponent was going to be positive. Okay, so that is 2. So 0.10000010. Okay, so I'll stop the vid there and then we'll do the arithmetic. Is everyone happy with those?